In a world where the boundaries of science fiction blur with reality, NASA has once again done the unimaginable. They've developed and built the near impossible, a light-speed engine. This is neither science fiction nor fantasy. This is the culmination of decades of tireless research, innovation, and unwavering determination. NASA, the wizards of the cosmos, have created a propulsion system that can push the boundaries of our understanding of physics, a technology that can transport us to the farthest reaches of the galaxy in the blink of an eye. But how is this even possible, and what mysterious forces have they harnessed? Join us as we take you behind closed doors and deep into the heart of NASA's top-secret research as we uncover how NASA now develops and builds its iconic and near-impossible light-speed engine. The speed of light. Light speed, as the name suggests, is the astonishing pace at which light races through the vastness of space. An engine operating at this speed will be capable of zooming across the vast expanse of space at an astonishing 671 million miles per hour, a speed that's incredibly difficult to grasp. This velocity is unmatched in the universe, making it the ultimate speed limit, a consistent and unchanging force of nature. In the intriguing realm of physics, only specific kinds of waves, such as light, radio waves, and gamma rays, can match this blazing speed in a vacuum. These waves are peculiar, known as massless particles, because they possess no resting mass. This peculiarity grants them the ability to effortlessly soar at light speed, gracefully gliding through the vacuum of space without any resistance or obstacles. Conversely, particles with rest mass, like protons, electrons, and atoms, no matter how much force you exert, can never outpace light. They're forever destined to lag behind, similar to a cosmic tortoise compared to light's unyielding hair. Interestingly, scientists often use light speed as a benchmark to measure other velocities in the cosmos. For instance, when determining how swiftly an object is moving through space, they gauge its speed relative to this cosmic champion. It's similar to comparing a snail's crawl to a supersonic jet. Light speed is undoubtedly the cosmic speed limit, standing as the absolute maximum pace at which anything, whether it's energy, matter, or information, can venture across the immense expanse of the universe. It remains an essential and unchanging principle of nature. The concept of light years. The monumental challenge of sending humans into space arose from the sheer vastness of the cosmos. Scientists tackled this cosmic enormity by introducing the concept of light years, a unit used to measure these colossal distances. A light year, a term that describes how far light can travel in a year, spans an astounding 6 trillion miles or 10 trillion kilometers. To put it in perspective, it takes just 1 second for light to journey from the moon to our eyes, so the moon resides a mere light second away. On the contrary, sunlight, which is vital to our existence, takes approximately 8 minutes to reach us, placing the sun at a distance of 8 light minutes. Consider Alpha Centauri, our nearest neighboring star system. It dwells at a staggering 4.3 light years away. Beyond our solar system, objects can be found billions of light years apart. This phenomenal gap leads astronomers to peer back in time when they observe these distant objects. Unwavering in their pursuit, scientists have sought ways to achieve mind-boggling speeds for space travel. And with Elon Musk's SpaceX envisioning a future where Mars is colonized. Yet the journey to the red planet currently consumes several months, or even close to a year, contingent on planetary alignments. In stark contrast, traveling at the speed of light would shrink this expedition to less than 4 minutes. Alas, achieving such speeds necessitates an astonishing amount of kinetic energy, making even a minuscule fraction of light speed a Herculean feat. Now it's time for today's subscriber pick. In a world not far from our own, NASA embarked on an unprecedented journey to break the boundaries of space travel. After decades of relentless research and tireless experimentation, they accomplished the near impossible, the creation of a light-speed engine. It was a breakthrough that would change the course of human history. The engine, aptly named Luminary Drive, was a marvel of cutting-edge engineering and scientific ingenuity. With sleek, aerodynamic lines and a silver sheen that seemed to shimmer in the light, it represented the epitome of human achievement. Scientists and engineers stood in awe as they beheld their creation, the key to interstellar travel. The Luminary Drive worked on a revolutionary principle, harnessing the power of cosmic energy to propel the spacecraft at an astonishing speed. It was a blend of advanced physics and technological wizardry, a masterpiece that defied the laws of conventional physics. The engine promised to send astronauts hurtling through the cosmos faster than the blink of an eye, opening up a universe of possibilities. As the world watched in anticipation. NASA prepared for the inaugural flight. Astronauts, chosen from among the bravest and most skilled, underwent intensive training. They were about to embark on a mission beyond the realms of imagination, a mission that would propel humanity into a new era of exploration and discovery. The countdown began, echoing the heartbeat of a planet ready to reach for the stars. The luminary drive hummed with potential, a symbol of mankind's insatiable thirst for the unknown. The future was now within reach, and the world held its breath in awe and wonder. What do you think about this? Please share your thoughts on this matter in the comments below. The M-Drive thruster. In the realm of space travel, an extraordinary engine has emerged, one that promises to propel spacecraft without the need for traditional fuel and leaves no exhaust in its wake. This mystical contraption is known as the M-Drive, aptly nicknamed the Impossible Engine, for its audacious claim to defy the laws of physics. At first glance, the M-Drive resembles a conventional rocket engine, but upon closer inspection, you'll notice a peculiar absence of openings. Its ingenious operation relies on the intricate dance of microwaves confined within a sealed chamber. These microwaves, bouncing off the chamber's walls, orchestrate a phenomenon that seems to create a propulsive force. This innovation represents a seismic shift because every other form of rocketry hinges on the principle of momentum conservation. In simpler terms, for any object, including spacecraft, to move forward, it must push off something else. Think of it like jumping. Your feet push against the ground. An airplane surges ahead by pushing against the air, and rockets rely on expelling exhaust gases to thrust themselves forward. But the M-Drive stands apart, defying this conventional wisdom. It operates as a mere container, where microwaves ricochet within, seemingly propelling the engine itself forward. This confounding capability is precisely why it earns its title as the Impossible Engine. The enigma of the M-Drive delves into the depths of physics, taking us beyond our current grasp of the laws that govern the universe. It's a riddle that baffles scientists, for no one truly comprehends its inner workings. Some ponder whether our current understanding of physics is incomplete or flawed, while others anticipate that testing this device might unveil hitherto undiscovered realms of physics. The inception of the M-Drive dates back to 2001, and in the years since, various research groups have claimed to measure a net force emanating from these enigmatic contraptions. Yet, the effect they've observed is infinitesimally minuscule, incapable of nudging even a sheet of paper. After nearly 2 decades of experimentation, we find ourselves in possession of a collection of results that fail to command attention or provide a clear elucidation of their mechanisms. While skepticism looms large, with some experts dismissing the M-Drive as a futile endeavor, the allure of this unconventional technology persists. It remains conceivable that our existing understanding of physics, or uncharted territories of physics yet to be explored, could hold the key to unlocking the mysteries behind this perplexing device, making it a tantalizing frontier for future research and discovery. The warp drive. The concept of the warp drive, once relegated to the realms of science fiction, has begun to reveal its potential as a reality. Dr. Eric Lentz, a seasoned physicist, has dedicated his efforts to transforming this fantastical notion into a practical possibility. While he was not the trailblazer in this endeavor, his work holds immense promise, with the potential to reshape our understanding of the universe and revolutionize space travel as we know it. Our journey into the warp drive phenomenon can be traced back to 1994, when Mexican mathematician Miguel Alcubierre ignited the discussion. His visionary proposal, now recognized as the Alcubierre warp drive, emerged not as a spaceship propulsion blueprint, but as an exploration of the theoretical frontiers of physics. Alcubierre's trailblazing inspiration draws from Albert Einstein's revolutionary general theory of relativity, a cornerstone of modern physics. Einstein's groundbreaking theory revealed that space-time is not a static backdrop, but rather a dynamic fabric that can warp and bend in response to the presence of energy and matter. This profound revelation upended our perception of the universe. Alcubierre's brilliance lay in pushing these theoretical concepts to their limits. He pondered whether it was conceivable to manipulate space-time, creating a shortcut through the cosmos that would enable faster-than-light travel. His visionary framework involved crafting a warp bubble or warp field around a spacecraft. Within this field, space-time would undergo a specific warping process, compressing space behind the ship while expanding it in front. This manipulation would generate propulsion effects, all without relying on conventional rocket propulsion methods. It was similar to discovering a method to to surf upon the undulating waves of space-time curvature. What made Alcubierre's groundbreaking work truly exceptional was not just its audacious nature, but its mathematical legitimacy as well. It represented a valid solution to the venerable Einstein field equations, the bedrock of general relativity. In essence, Alcubierre's idea was a legitimate interpretation of Einstein's theory, despite its reliance on speculative concepts like exotic matter with negative energy density. This groundbreaking proposal flung wide open the doors to dialogues surrounding the potential for faster-than-light travel, a concept long relegated to the realms of science fiction. Alcubierre's work commanded the attention of both the scientific community and ardent science fiction aficionados, sparking extensive discussions and impassioned debates. However, a formidable hurdle looms on this hypothetical path to warp drive realization: the necessity for exotic matter with negative energy density. This elusive substance remains a tantalizing enigma, a puzzle piece yet to be discovered or understood. This exotic matter stands as the linchpin in the warp drive's intricate mechanism, essential for creating the elusive warp bubble that bestows spacecraft with the ability to journey at warp speed. However, the enigma lies in the fact that exotic matter remains purely theoretical, an ethereal substance never observed in the natural world. In addition, the energy demands of a warp drive are staggering, bordering on the unimaginable. Alcubierre's initial calculations painted a daunting picture. To propel even a moderately sized starship at warp speed would require more energy than the entire observable universe contains. Subsequent studies have endeavored to reduce this astronomical energy requirement, but the chasm between theory and practicality remains vast. Interestingly, warp drives harbor the potential to conjure closed time-like curves, giving rise to perplexing time travel paradoxes such as the notorious grandfather paradox. The resolution of these temporal conundrums presents an imposing challenge. Nonetheless, recent developments have reignited hope for the realization of warp drives. The Advanced Propulsion Laboratory at Applied Physics has put forth a novel model that diverges from previous concepts relying on negative energy or exotic matter. This innovative approach leverages the behavior of space-time bubbles to achieve warp-like travel. In the years ahead, researchers will strive to refine the Alcubierre warp drive, addressing its colossal energy prerequisites and confronting the enigmatic paradoxes entwined with time travel. The scientific community, ever captivated by the tantalizing prospects of warp drives, persists in grappling with the theoretical nuances, pondering whether this extraordinary propulsion system can one day transcend the boundaries of theory and become a genuine reality. Chemical rockets, while undeniably effective, may appear somewhat rudimentary upon closer examination. Their operation is surprisingly straightforward. You load up vast quantities of fuel, either in liquid or solid form, add an oxidizer, ignite the mixture, and harness the resulting explosive gases to propel your rocket in the desired direction. However, despite their effectiveness, they suffer from a fundamental inefficiency. Take, for instance, the Falcon Heavy, a colossal space-bound behemoth, weighing a staggering 550 metric tons. To lift off, it carries nearly 400 tons of fuel and oxidizer. The first stage burns for a mere 162 seconds, followed by the second stage lasting 397 seconds, culminating in a total burn time of approximately 9.5 minutes. This inefficiency has spurred scientists and engineers to seek alternative propulsion methods, particularly for extended voyages into the cosmos. In the quest for more efficient propulsion systems, researchers have explored a multitude of possibilities, from ion drives that use electricity to accelerate particles to nuclear thermal propulsion, which taps into the immense energy of nuclear reactions. The ion thruster. Alcubierre's visionary proposal has not only ignited our imaginations, but also propelled us toward the development of groundbreaking propulsion concepts, notably ion drives and warp drives. Among these innovations, the ion thruster stands out as a promising solution for space exploration. Ion drives, while relatively slower than some alternatives, boast unparalleled fuel efficiency. This makes them an attractive choice for a variety of space missions. Unlike traditional chemical rockets that expel hot gases at around 5 kilometers per second, ion engines kick it up several notches, propelling individual atoms at a staggering speed of 90 kilometers per second. This velocity upgrade translates into significantly more efficient acceleration, while chemical rockets typically operate at an efficiency rate of approximately 35%. Ion engines shine with an impressive 90% efficiency. What's more, these engines can operate tirelessly for days, weeks, or even months, delivering thrust long after their chemical counterparts would have depleted their fuel. goal. Once a spacecraft escapes the gravitational pull of a planet, ion engines become exceptionally efficient tools for making remarkable changes in velocity. NASA and other space agencies have wholeheartedly embraced ion engines across various missions, yet they've remained on the lookout for even better propulsion options. The development of ion thrusters has been a labor of decades, marked initially by caution due to potential risks. A game-changing moment arrived with NASA's Deep Space One mission, launched boldly in 1998. This spacecraft was a treasure trove of daring technologies, boasting low-power electronics, solar concentrator arrays, scientific instruments, and a cutting-edge solar electric propulsion system. This novel engine ran for extended periods, enabling it to embark on up-close observations of asteroids, comets, and even Mars. Building on the triumphs of Deep Space One, NASA's Dawn mission took propulsion to the next level. Equipped with not one but 3 redundant ion engines, this spacecraft performed astonishing feats. These engines empowered Dawn to orbit the asteroid Vesta, gather invaluable data, and then elegantly break orbit to set course for asteroid Ceres, embarking on a journey of even more exploration. To grasp the sheer acceleration these ion engines provide, consider this. Dawn can accelerate from 0 to 100 kilometers per hour in a mere 4 days of continuous thrusting. Ion thrusters have proven invaluable in a multitude of missions, showcasing their versatility and potential. For instance, ESA's Smart 1 spacecraft utilized ion engines to journey from Earth's orbit to lunar orbit, demonstrating the adaptability of these engines. In a similar vein, the Japanese Hayabusa spacecraft heavily relied on ion engines for its mission. The robustness of ion engines has been underscored through rigorous Earth-based testing, where they operated continuously for an impressive duration of over 5 years, attesting to their durability and endurance. Looking ahead, the future holds exciting prospects for ion thrusters. Researchers are fervently exploring avenues to enhance their performance. One promising approach involves a substantial increase in the electricity used to accelerate the ions, potentially boosting their output and efficiency. Notably, NASA once envisioned a mission called the Jupiter Icy Moons Orbiter, powered by the nuclear-electric xenon ion system engine, which could have utilized ion thrusters to explore Jupiter's moons. Although this mission was regrettably canceled in 2005, the vision continues to inspire ongoing advancements in ion thruster technology. Another avenue involves the development of high-thrust versions of ion engines, exemplified by NASA's X-3 Hall thruster. Capable of producing 5.4 newtons of force, a substantial leap from the previous thrusters, this technology could drastically reduce flight times for human astronauts traveling to Mars, potentially shortening the journey to just a few months. Engineers are eagerly preparing for 100-hour tests of the X-3 to evaluate its long-term operational capabilities, offering a glimpse into the exciting future of ion thrusters. The European Space Agency is on the cutting edge of propulsion technology with its air-breathing ion engine. Instead of carrying bulky propellants, this innovative engine draws in air molecules from the Earth's atmosphere in low Earth orbit, ionizes them, and then expels them as a propellant source. What makes this development particularly exciting is the spacecraft's access to abundant solar electricity and atmospheric propellant. This combination enables these spacecrafts to operate for extended periods without the need for refueling. This advancement holds the potential to revolutionize space travel. Spacecraft equipped with air-breathing ion engines could function at lower altitudes, expanding our reach within the cosmos. Space stations could remain in low Earth orbit indefinitely without requiring periodic boosts, marking a significant shift in the way we conduct operations in space. The innovative concept of utilizing the Earth's own atmosphere as a resource offers a promising glimpse into the future of sustainable and cost-effective space exploration. The ion drive. Space exploration has witnessed the resurrection of once-dismissed concepts, and the ion drive is a prime example. Initially deemed fit only for the realms of science fiction, the ion drive has firmly established its credibility as a propulsion system. When the notion of an actual ion drive was first introduced, skepticism abounded. Critics questioned whether it could generate enough power to propel a small spacecraft. Yet, the ion drive not only functions but excels. In a remarkable display of its potential, NASA awarded a $67 million million contract to Aerojet Rocketdyne in 2016. Their mission, to design, construct, and test an advanced solar electric propulsion system, succinctly named the Solar Electric Propulsion (SEP) system. This cutting-edge system, also referred to as the Hall effect thruster, employs an electric field to accelerate propellant. Its efficiency and power represent a significant leap forward in space propulsion technology. The ion drive operates by first converting solar power into electricity. This electricity is then used to accelerate ions, charged particles, out of a nozzle, creating a forward thrust. Remarkably, scientists and engineers have been perfecting this technology known as solar electric propulsion for over half a century. Ion thrusters are currently in use on various spacecraft, exemplified by NASA's Dawn probe, now in orbit around the dwarf planet Ceres. There are ambitious plans to implement the SCP drive for future missions to Mars. However, one limitation of the ion drive is that it imparts a very small amount of momentum to the spacecraft. Despite this, ion drives shine in the realm of fuel efficiency. Among all spacecraft propulsion methods, they stand out for their exceptional fuel efficiency, making them a desirable choice for long-duration missions. NASA is actively embracing high-power electric propulsion systems, exemplified by their application in the Lunar Gateway, a space station that will orbit the Moon. In April 2021, NASA demonstrated progress by firing up an ion thruster system that displayed a 30% increase in power compared to previous designs. This signifies a significant leap forward in propulsion technology, paving the way for enhanced space exploration capabilities and potentially faster and more efficient journeys to celestial destinations, including our lunar neighbor and beyond. The continuous advancements in ion thruster technology underscore our growing capacity to unlock the mysteries of the cosmos. Nuclear thermal engines. NASA's pursuit of cutting-edge propulsion has shifted its focus from ion thrusters to nuclear thermal engines, marking an exciting leap in space propulsion technology. A notable collaboration between NASA and DARPA, known as the Demonstration Rocket for Agile CIS Lunar Operations, or DRACO, is currently underway. The primary goal of DRACO is to accelerate the development of advanced nuclear thermal propulsion technology and to have it operational by 2027. These nuclear thermal engines have the potential to revolutionize space travel, enabling astronauts to traverse deep space at remarkable speeds. Compared to conventional methods, nuclear thermal rockets significantly reduce travel time, especially when embarking on lengthy journeys like those to Mars. This time reduction is pivotal, as it simplifies logistics by requiring fewer supplies and less complex systems. Moreover, nuclear thermal rockets offer added advantages beyond speed. They enhance the capacity for scientific payloads, provide increased power for instruments and communication systems, and streamline space missions. At their core, these rockets utilize a fission reactor that generates extremely high temperatures. This heat is then transferred to a specialized liquid propellant. Upon release through a nozzle, the propellant expands and propels the spacecraft forward, achieving propulsion in a highly efficient and technologically advanced manner. In fact, nuclear thermal propulsion can be up to 3 times more efficient than traditional chemical propulsion methods. The importance of the space domain has never been more profound, as it touches upon a wide array of aspects, from commerce to scientific exploration and national security. Within this context, the strides made in space technology through the DRACO nuclear thermal rocket program hold tremendous promise. These advancements are poised to revolutionize the transport of materials to the Moon and eventually facilitate human missions to Mars. It's crucial to recognize that the last time the United States conducted nuclear thermal rocket engine tests was over half a century ago. Thus, this collaborative effort marks a monumental leap forward in space nuclear technology. Recent breakthroughs in aerospace materials and engineering are ushering in a new era, setting the stage for the emergence of an Earth-Moon economy. However, the collaboration doesn't conclude with DRACO. NASA, alongside the Department of Energy, DOE, and industry partners, is engaged in a multifaceted endeavor to harness nuclear power for space exploration. Together, they are devising concepts for nuclear power plants capable of operating on the Moon and Mars. These initiatives align with a broader strategy aimed at enhancing engine performance and supporting long-term objectives in the realm of space exploration. The shift from ion thruster engines to these new nuclear developments might raise eyebrows, as it seems to defy the laws of physics. However, this transition is not driven by whimsy, but rather by the recognition of the limitations of ion and plasma thrusters. Ion and plasma thrusters have their merits, but they grapple with substantial drawbacks. A primary concern is their notably low average thrust, which pales in comparison to the forceful propulsion propulsion delivered by traditional chemical rockets. The meager thrust output hinders their ability to accelerate quickly. Another challenge lies in the voracious appetite for electrical power exhibited by ion and plasma thrusters. These systems demand substantial energy, ranging from tens of kilowatts to multiple megawatts. To put it in perspective, this is akin to continuously running a high-powered, electricity-hungry appliance in space. Generating and storing such vast amounts of electricity in the cosmic vacuum is no trivial task. Moreover, ion and plasma thrusters bring with them the looming specter of contamination. They pose a risk of contaminating the spacecraft's exterior with substances like mercury or cesium. Such contamination can wreak havoc on sensitive instruments and equipment aboard the spacecraft, potentially impairing their functionality. In contrast, nuclear thermal engines offer a decisive advantage in terms of thrust when compared to ion thrusters. These engines provide the burst of power necessary to propel a spacecraft swiftly, particularly when liquid hydrogen, LH2, is utilized as the propellant. This shift is rooted in a pragmatic approach to addressing the challenges and optimizing space propulsion for efficient and reliable interplanetary travel. These advanced engines possess some impressive features. They boast a higher specific impulse and greater exhaust velocity compared to traditional chemical rockets. This translates to better efficiency because spacecraft can cover more distance while using less fuel. However, it's important to note that while it's more efficient, it's not a quantum leap in efficiency in a vacuum. Nuclear thermal engines offer a unique advantage. They have the potential to reduce the empty weight of the vehicle and increase the payload percentage. Think of it as the engines shedding excess baggage and optimizing their cargo space. This feature proves especially beneficial for long-distance missions where every kilogram of payload matters. In essence, while ion and plasma thrusters have their own merits, nuclear thermal engines step in with their higher thrust capabilities and efficiency advantages. It's all about selecting the right tool for the job and carefully weighing the pros and cons to ensure space missions succeed. However, these engines aren't without their challenges. Once the nuclear core is up and running, approaching it becomes a risky endeavor. It and the surrounding support structures become intensely radioactive. This means crew members and most robots can't get anywhere near it. They must maintain a safe distance of several hundred meters, which adds to the overall weight and complexity of the spacecraft. Beyond radiation concerns, there are other issues this rocket engine poses, but scientists are diligently working to make it better. A collaboration between NASA and DARPA aims to make space missions more efficient and set the stage for a new era of space exploration. These advancements in propulsion technology hold the promise of unlocking the vast potential of deep space. By harnessing the power of nuclear thermal engines, we can venture farther into the cosmos, carrying heavier payloads and pushing the boundaries of human exploration. While challenges persist, our relentless pursuit of innovation will pave the way for a brighter future among the stars. Which of these light-speed engines do you think will eventually be endorsed by all? Please share your thoughts in the comments section.